Hello, this is Mr. White, and this video is all about using calculus, more specifically summations and ultimately limits, to compute the area of a plane region. And if everything is going according to my current plan, we've already done this in class, and you probably found it a little bit overwhelming and intimidating. So the purpose of this video is to just let you see it again, fill in some of the gaps that you may have missed the first time around. Okay, so for this example, find the upper and lower sums for the region bounded by the graph of f of x equals negative x squared plus 4x plus 1, and the x-axis between x equals 0 and x equals 4. That's a mouthful. Now, I just used the same wording that the current version of our textbook uses, but I probably mentioned in class that I don't really understand why the book focuses so much on upper and lower sums. For this type of computation that we're doing right now, we deal more with left and right sums. And for this example, I'm just going to do the right sum. So as a quick reminder of how those all compare, upper, lower, left, right sums, here is a GeoGebra depiction of our examples function. And the lower sum is the one with all those n rectangles. In this case, I have n equals 5. So the n rectangles are crammed underneath the curve. For an upper sum, the n rectangles are just slightly a little bit too big, above the curve. And for a left-right sum, I have it set to a middle sum right here, but if I set it to a left sum, we see that the curve goes through left-hand corners of each individual rectangle. And we notice that when we have a function that changes direction, in other words, like this one that goes from increasing to decreasing within that interval, we notice that these left sum rectangles started out also being not just left rectangles, but they're also lower rectangles, right? But then when the curve changed direction, they switched. They're still left rectangles, but they switched to being upper rectangles as well. And if I make it a right-hand sum, such as we're going to do in the actual example, we see that it started out not just being right-hand rectangles, but they're also upper rectangles. And then when the curve changed direction, they became lower rectangles. And the good news for you, it's all confusing, and if this graph had went from decreasing then to increasing, that would have changed all things around. But the good news is for you is that if we want to find the exact sum, it's not going to matter what we use, or the exact area under the curve. It's not going to matter whether we use the upper, lower, left, right sum, whatever. We see that if I were to display all three sums, the little graph on the right shows, you see that I have the actual values of the right, upper, and lower sums displayed here when n equals 5. And we find that when I change the value of n, you see that the graph on the right here reflects the fact that all three of those sums are now converging. They are asymptotically converging to the same value. So when we ultimately take the limit of our right, upper, or lower sum, it doesn't matter which one we use, they all are going to have the same limit. All right, so let's go back to the example. We're going to find the right sum, we said. So this is such a visual topic, you really have to draw a picture, I'm going to say. And our picture was of a parabola that increased and then decreased. And let's say that this is 4 right here. And we need to divide this into a bunch of n rectangles, and we're going to make it a right sum. So let me draw those as right sum rectangles. Notice it's going through the right corner of the rectangle. And I'm not going to worry about exactly how many rectangles I draw. I need to remember that it represents n rectangles. And in fact, let me just do a dot, dot, dot. And then I'll pick up here and again do some right rectangles. And there we have it. There are our right rectangles, and there are n total rectangles. So let's fill in some more information here. This is a total width. This interval has a total width of 4, and there are n rectangles, right? So each individual rectangle has a width of 4 over n. Etc., 4 over n. So rather than just focus on the individual widths, though, that is important, but we also want to know what are the x-coordinates. How has this x-axis been split up by those rectangles? So do these x coordinates. It's going to get a little bit crowded here, but let me call this coordinate. It's only one rectangle over, so its x value is 4 over n times 1. When I go 2 rectangles over, that has an x coordinate of 4 over n times 2. And yes, I could multiply it out and call it 8 over n, but I'd rather see the pattern. 4 over n times 3. Especially for this process, that's going to be really useful to us. 4 over n times 3, I can keep going. And the last one, rather than just write that as 4, I'm going to say 4 over n, and it's the nth rectangle, so times n. And if I want to, and I do want to, I'm going to put 4 over n. The one right before it would be n minus 1. And OK, I think that's enough. All right, so I hope you're not viewing this on a little mobile phone. I need to shrink this picture down. So hopefully you're viewing this on a tablet or a full desktop or laptop. So let me shrink that down. And let's go ahead and figure out how we're going to compute this area. I'm going to say that the right sum, I'm going to use S for sum, and I'll put a little subscript of right. The right sum is going to be the sum of all these rectangles from the first rectangle all the way up to the nth rectangle. And I want to add the individual areas of these rectangles. So how do I compute the area of a rectangle? Well, that's base of the ith rectangle times height. Almost running out of room, but I think I'll make it there. The height of the ith rectangle. OK, the base will be pretty easy here. I'm going to do my lazy thing. I'm not going to bother to write the n and the I equals 1 on the sigma. I'll just stick with the sigma sign until I need the n and the I value. The base of every rectangle, we already said, that's 4 over n. The height's a little more tricky. We need this function. That's what dictates the height of each rectangle. So notice that the height of the first rectangle was dictated by this first x value. The height of the second rectangle was taking the second x value and plugging it into the function, and so on. Notice that this is working because it's the right sum. Notice that if it was the left sum, I would have had to start with 0. If that didn't make sense, I'm going to ask that you just come to office hours, and I'll explain that further. But I'd be doing things a little bit differently if I was dealing with the left sum. But for the right sum, I'm going to say that the height is dictated by taking the ith x value. And let me just temporarily, realize I forgot to do something. So let me just temporarily call that x sub I, and then come back over here to the left and do what I forgot to do. This first rectangle, this first I value, x value was, I'm going to call that x sub 1. That was 4 over n times 1. This second x value, I'll call it x sub 2. That was 4 over n times 2, right? So hopefully you're quickly seeing the pattern. And I'm going to say that just in general, the ith rectangle has an x value of 4 over n times whatever I is, right? So that's what I'd forgotten to do. That's what I really wanted to plug in on this equation over to the right. So I'll tell you what, I'm going to go ahead and just delete where I have x sub I and write in there 4 over n times I. Those are the actual x values that I need to plug in. OK, so let me shrink this down a little bit. I'm going to do one more step on here, and then I'm going to move to another screen. I'm going to go ahead and plug this x value, or these x values, that represents a lot of values, into the function equation. So this summation equals sigma 4 over n. I'm trying to eke out a little bit more space here. And it's going to be negative x squared. So let me do negative. And remember, x is really 4 over n times I squared plus 4x plus 4 times x. Once again, 4 over n times I plus 1. Close parentheses. All right. I feel like this is we've done the hardest part. Believe it or not, we've done the hardest part. Setting it up, I believe, is the most difficult part of the whole process. So since I'm going to move to another page, let me go ahead and put in the I equals 1 and n as a formality. And let's switch over to another page. So if there's anything that if you need to pause and just kind of let that soak in, do what you got to do, because at this point in the video, I'm going to move on to the other page. Okay, let's continue. All right. For some things that we do, I might want to bring this constant to the outside, but you know, for this particular process, I'd rather not. Oops, looks like I lost my n up there. I'd rather not. Since this is pretty much algebra from here, I'm going to go a little bit quickly. Again, pause the video as needed. I'm going to go ahead and expand that out. I'm going to say that that's, I'll go ahead and write the 4 over n. I was trying to decide whether to distribute that in my head or not, but let's call that negative 16i squared over n squared plus 16i over n plus 1. And obviously you have to be careful. There's some really silly and easy algebra mistakes to be made. But again, I'm going to take a little bit of a shortcut and trust that you're getting used to some of the nasty algebra. We know that ultimately I'm going to want to split this up into just a sigma I squared, right? And I need to ask myself, what's going to be on the outside of that sigma? Well, look at all those constants. So that's going to all amount to a negative 64 over n cubed. And I know that for the next sigma, I want just an I on the inside. So I have to keep in mind that the 4 over n is still applicable, as well as those constants. So that's going to amount to a 64 over n squared. And for the last one, that one's pretty tame. I'm just going to put sigma 1 with a 4 over n to the outside. All right, I find at this point I like to just stop and check. And notice a little pattern here. Notice that for I squared, there's an n cubed on the bottom. For I to the 1 power, there's an n squared. And for I to the 0 power, there's an n to a 1. That's not coincidental. So just observe, see if you can see the significance in that. In the next step, we're going to go ahead and plug in our formulas. So remember the formula for I squared is, and again, all these sigmas are from 1 to n. So the formulas apply. And the formula for I squared was n plus 1, 2n plus 1 over 6. Let me go ahead and just do all the formulas at this point. The formula for I was n plus 1 over 2. And the formula for just a constant, in this case 1, was constant times n. In this case, that's just 1 times n. OK, let me fill in the rest here. Negative 64 over n cubed plus 64 over n squared plus 4 over n. So we reach another point where pause the video if you need to, soak it all in, because I got to go to a new page here. OK, let's simplify some of this. And here's where we just have to be very careful and avoid some careless algebra mistakes. I'm going to take a 6, I'm going to divide that by 2, and I'm going to divide this by 2. And let's just call that let me get rid of this n and call this n squared. I think that's enough. Let's call that negative 32. And let me go ahead and distribute out those binomials. Call that 2n squared plus 3n plus 1 all over 3n squared. I think I got that right. OK, let's move on to the next one. 64 and 2, both divided by 2. Again, handle the n's, make that an n. And let's call that plus, I'm going to go ahead and distribute that 32 and call that 32n plus 32 all over n. And I know I'm going really quickly through the algebra. Pause the video if you need to. Make sure you can hang. The n's here cancel, and that's just plus 4. OK, let's distribute out that first term real quickly. Let's make that negative 64 n squared minus 96 n minus 32 over 3n squared. And I could do like denominators, common denominators, and all that stuff, but I'm going to do a different thing. Can you perhaps anticipate what I would do instead of combining these all using like denominators? Instead, I'm going to just go term by term and break it up. This is not one of those cases where I need a single term. So negative 64n squared over 3n squared would give me negative 64 thirds. Minus 96n over 3n squared gives me minus 32 over n. And then finally, minus 32 over 3n squared plus 32n over n just gives me 32 plus 32 over n plus 4. And we're almost finished, but I just need a little bit more room. So let's copy onto a new page here and finish this off. All right, now it's time to just combine the like terms, right? So negative 64 thirds. Notice I'm starting with the constants. Your inclination may have been to start with the n squareds and then the n's, but notice that the n squareds and the n's are in denominators, so they are not the highest degree terms. All right, so if I combine those three constants, I would get, let's see, 44 thirds. And then if I go on to the over n terms, those just happen to cancel out. Most of the time that doesn't happen, but in this case, those two just canceled out. And then finally, minus 32 over 3n squared. And that, ladies and gentlemen, is our right-hand sum. And just to make absolutely sure that we understand what we've accomplished with this formula, let's plug in a couple values of n using our calculator. Let's calculate a couple values of our right sum for n equals 5. That's just an arbitrary choice of mine. So I plugged in n equals 5, and I got 14.24. Then I plugged in n equals 10, again arbitrarily, and got 14.56. If I bring back my GeoGebra model here, I see that for n equals 5, you look in the upper right-hand corner of your screen, and you see that the right sum is indeed 14.24 for n equals 5. If I scroll this out to n equals 10, we see that the right sum is indeed 14.56. So we verified that our formula, that we did everything correctly. Now, I have one more small thing to do, and the good news is that it's a very quick and easy step. We're obviously really not interested in just these right sums. We're interested in the actual area underneath the curve, not just the area of these little rectangles. So the last thing we'll do here is ask the question, what if we use the results from the previous example to what is the exact area of the region? So that's just the same region that we just worked with. So let me paste the results that we just got. And I'm guessing that you know what's coming up, but let's just take it as let's just do this as a formality. The actual area of that region is going to equal the limit of, in this case, the right sum. But again, I emphasize that that could have been the left sum, the upper sum, the lower sum. Any of the sums will give us the same limit. We're going to take the limit. We're going to ask what happens as we increase the number of rectangles under that curve or over that curve to infinity. And in this case, limit as n goes to infinity of 44 thirds minus 32 over 3n squared. We see that this term would just go to 0, and our actual area, and this is not an approximation anymore, this is the exact area underneath that parabola, is 44 thirds. Pretty cool, huh?